Hello everyone, this is Mustafa here, solving soil mechanics problems for civil engineering students. In this video, I'm talking consolidation, and we have here question number 4. Let us see what we've got. We are given a soil profile. This is a soil profile. We have two clay layers. One is called soft clay and one is medium clay. And extracted at point A and point B were two samples, and they underwent some sort of consolidation testing, and these are the results of the consolidation test. We are advised here that there will be a future 4-meter thick fill compacted that will be placed on top of the ground surface here. Required is to determine the total consolidation settlement of the two clays, clay top and the clay bottom. Let us see the solution strategy for a problem of that nature. First is to determine the in-situ stresses sigma dash V naught at strategic locations. In this case, it's point A and point B. Then we determine whether each clay is normally consolidated or over-consolidated. The normally consolidated soil is the one that has never seen any stress greater than the present value. The over-consolidation is the one that saw stress value in the past greater than the present value. And then once we determine whether the soil is normally consolidated or over-consolidated, we should use the right formula. Essential knowledge: we need to know how to determine the in-situ stress at any point within any soil profile. And then we need to know how to apply the settlement equations, whether the soil is normally consolidated or over-consolidated. Let me quickly review with you the situation here if we have normally consolidated or over-consolidated soil. So when I have a soil of thickness H, I need to determine whether it's normally consolidated or over-consolidated. If the soil is virgin, normally consolidated, never saw anything greater than the present overburden pressure that's experiencing as we speak, so any settlement or any compression of any soil sample will actually move along that line. Gradient is C sub C, the compression index, and you have here initial void ratio E naught. A point A will compress to point A dash, and this will experience a reduction in the void ratio delta E due to pressure increment. We call it here delta sigma dash V naught, and the formula that will represent this settlement is written here. You can review my previous videos. So ST is the compression index divided by 1 plus E naught times the thickness of the layer, H in this case, log the final stress value, which is that point, divided by the initial stress value, which is that point. If the soil experienced some sort of unloading in the past, it means that when the stress state reached that point in the past, some sort of unloading happened along that red curve here, the gradient of which is CR, or the recompression index. Some people call it the swelling index. And then if another reloading takes place, it should happen along this red line, and the equation that governs the settlement along this recompression curve is this formula, which is exactly like the one for the normal compression soil, but in this case we replace the compression index C sub C with the reloading index, or the swelling index, we call it CR. The right term is the recompression index in this case. Anything else or everything else being the same. So let us see how we can apply this to our problem. First, this top clay is 6 meter, bottom clay is 3.1 meter. 6 meter and 3.1 meter are relatively thick soils, and it's a good idea if we want to calculate some sort of accurate settlement is to divide it into sub-layers. So I opted here to divide the 6 meters into 3 sub-layers. Each of them would be 2 meters, 2 meter thick for each of these 3 layers, and these red circles represent the middle within each sub-layer. Likewise for the bottom clay, 3.1 meters, so I will have 2 layers. So let us start now calculating the in situ stress at point A, because we have an assumption here that point A and point B each represent the clay of interest. So let us recalculate the in situ stress at point A. At point A, I have here 3 meters times 14, which is this unit weight, 3 times 14. I add to this 2.1 meter, but now it's submerged. This is why I have a green here. And then I have 4.2 meter of submerged soft clay. So I take away from the 13.5 kilonewton per meter cubed, I take away the 9.8 kilonewton per meter cubed for the water. So now I calculated the in situ stress at point A being close to 74 kPa. The pre-consolidation pressure given at point A is 75 kPa. So 74 is almost equal 75. So we can claim that the clay is almost normally consolidated at this point A. So now we decided on the nature of that clay. At point B, we repeat the same process. So I have 3 meter, this is point B, 3 meters times 14. Then I add 2.1 meter of submerged unit weight, 17.5, take away 9.8. And then I have a full 6 meter here times 3.7, which is the submerged unit weight of that. I add to this 2 meter here within the medium clay times 5.2, and this has given me 90.77. Now we are in a position to do the comparison. So I have 90.77 at this point, that's overburden pressure. So I would compare it with the given value here for the pre-consolidation pressure 100 kPa. So it means that the present stress value at point B is less than the maximum past value of 100 kPa. So the clay at point B is also normally consolidated. Now we come to the fill pressure. I have here, it is said that the future fill will be compacted to 92% Proctor value. What is Proctor value? Proctor value is a dry unit weight that you get from the laboratory compaction test. So I'm advised that 92% of this value will be used in the field. This means that I multiply the 92% by the 19.4 to give me the dry density, or the dry unit weight here, because we are using kilonewton per meter cubed. The dry unit weight of the fill that will come atop the ground surface here is 17.85. But I'm advised that there will be moisture of 13%. So you need to consider the weight of this moisture as well. Based on that, I know that the bulk placed value of the fill unit weight is basically this formula. You need to know it, or it could have been given to you. So I multiply the dry unit weight times 1 plus the moisture content. It means that the bulk unit weight of the fill that will come here is basically 17.85 times 1 plus moisture content 0.13, that's 20.168. So now this tells me that this 4 meter of the fill will come here on top of the ground surface with a total unit weight of 20.168. So when I multiply the thickness by the unit weight, I would have pressure of 80.67 kPa. It will come here as a white surcharge on the ground surface. Because my two soils are deemed normally consolidated here, this is a formula that I will be using based on the normal compression curve that we saw before. So let us see how we can tabulate the data so that we can calculate the settlement. The strategy now is we have divided this clay into 3 layers. So I will calculate the settlement of each sublayer for this top clay. And they're gonna repeat the same for the lower clay. So the total settlement will be the summation of the settlement of each sublayer. So this will be the table. I will show you now how I have arrived at this table. So I have 5 layers. That's 1, 2, 3, 4, 5. Each of these circles, like I said before, represented the middle of each sublayer. So I have here the layer number, and I have the thickness of each one of those. So the thickness of this sublayer is 2, 2, 2, and for these 2 layers, the 4, 5, so I have 1.55 meter each. So I determined here, in the middle of each layer, the in situ pressure, effective, vertical. So I calculated this. I'll show you now one example. And then the pressure increment coming from the fill will be felt exactly the same anywhere here. And its value from the previous slide was 80.67 when we multiplied 4 by 19.4 times 1 plus the moisture content. And here I have C sub C divided by 1 plus E naught, so that I can use the settlement formula here, C sub C divided by 1 plus E naught. And then when I multiply all these terms together, so I get the settlement of the sublayer in question. And then I add them up. Let us try now for one of them. At point 1, sigma dash V naught, we need to perfect this. I have 3 meter times 14. And then I have 2.1 meter times the submerged unit weight here. And then I have 1 meter only, I'm interested in this sublayer, times 3.7. And this has given me 61.87. And this is the 61.87 kPa. And when I substitute here, C sub C divided by 1 plus E naught, C sub C is 0.59, that's 0.59 as you can see. And the initial void ratio 1.9, that's initial void ratio 1.9. So this has given me 0.203. I substitute here in this formula 0.203 times the thickness of the layer, that's 2 log 61.87 plus 80.67 divided by 61.87, and this has given me 0.147 meter. You need to be mindful of the units because we are using here meters for the thickness being 2 meters here. I repeat this for the rest of the sublayers, 1, 2, 3, 4, 5. I add them all, and this has given me 0.556 meter, or if you like, I have here the settlement 556 millimeter. So lots of lessons you learned from this. You need to review my previous videos, and you need to perfect how to calculate the in situ stresses at any point. You need to know how to determine whether the soil is normally consolidated or over consolidated, and the physical meaning of that. We need to know which formula to use to calculate the settlement, and then how to apply the formula and how to divide relatively thick layer into sub-layers so that we can get some sort of accurate estimation of the settlement. So I hope to see you next in more videos. Hopefully you have enjoyed this lesson.